And again, I will post the notes themselves so that you can look at them. Just need to change my camera here. All right. Now, yeah, that's better. Okay, so we're going to be considering what happens when you have a wave impinging on several narrow slits, and I'm drawing it as if it's just 4, and later on I'll do some math with 4, but we'll keep much of the math more generic than that. So imagine you've got a bunch of slits. They're separated by a distance a. Hecht actually uses d for that distance for some reason, but then later on he changes to a. So I'm just using a right from the start. And we're going to be looking off at some angle. So once again, imagine that we're far, far away from this and looking where the contribution from each of these comes together. We're going to make the assumption that these are tiny, tiny slits. So just as in the ripple tank, they diffract the wave out in all directions sort of equally. And so we're not going to worry about how the intensity changes with angle due to the individual slits. We're only going to look at how they interfere with each other. So we'll treat each of them essentially as a point source radiating in all directions. But they're coherent. They all are emitting their waves coherently, all in phase with each other. So if we're off at some long distance away, then these beams are essentially parallel, even though we would imagine them converging at that distant point. And that's where we would add up those contributions. And when we do that, we're going to find there's going to be a phase difference between these. And you can kind of see that drawn by these dotted lines here, showing that the upper beam, the zero beam, has to go through a bunch of extra path, and the lower ones don't have that. So the shift, the shift in phase is going to be according to that extra little bit there, and that's just a sine theta. A being the distance between the two slits, and then theta is the angle that we're looking at that becomes the same as the tiny angle in the triangle there. So that extra path is a sine theta. Turning that into a phase angle, if you just take that distance and divide by the wavelength, that's sort of then the fraction of the wavelength that that path represents. Multiply that by 2 pi, and you would have phase angle in radians. So 2 pi a sine theta over lambda would be the phase in radians. And then just realizing that 2 pi over lambda is k. So we can express that phase as ka sine theta. Now that's the phase change for just one of these. I'm not worrying about the sign here. I should, but I'm not. It doesn't really matter when we get to the end which direction you're working, whether this is an advance or a retarding phase. So I'm not going to worry about that. But do notice that each beam is shifted by that amount. And so if you're sort of comparing to beam 0, beam 2 would be shifted by twice that amount, beam 3 by 3 times that amount. So the phase for the nth beam would just be n times that phi that I've defined. So now as we go far away, we're going to be adding up the electric field from each of these. So we're going to be, you can draw this as a sum if you like, or write them out individually. I don't care which way you prefer to write this kind of thing. But then each one has this phase shift. And so, for instance, E1, as I've drawn it up here, would be E0 times this phase term, e to the I phi. That just shifts it by that phase of phi. The nth one would be E0 e to the I n phi, just multiplying it by this integer n that counts from one to the next. So what we've got now is a sum of terms, E0, then E0 e to the I phi, E0 e to the 2I phi, and so on up the line. You can write that in summation language over here if you like. We can factor out the E0, and what we're left with is this sum. And do you know what kind of a sum this is? You have a name for that? We call it a series, certain kind of a series.
Is that a Riemann sum?
Say that again, Ben.
Is that a Riemann sum?
Oh my. I guess I don't know. I think you're making it too
Oh.
complicated.
This is just like normal series, you know?
Yeah, there's a couple different kinds of series though.
Yeah, so this is just increase in power
Yes, it's
as we
changing
go.
by
So
power.
it's like, yeah, so we start 0, 1, 2, 3, like you wrote it.
No, you're changing them. Yeah, the power is going by 1, 2, and 3.
Yeah,
Just,
what I meant.
but that means the terms in the series are increasing by a factor.
Mhm.
It's what you call a geometric series.
Oh, that's true.
So a geometric series, and a geometric series has a known sum. I mean, that's been worked out long ago by somebody, not me. And so if you've got a geometric series like this, then with n terms, then that's the sum. It's 1 minus e to the, well, this is really just the factor that goes from one term to the next to the nth power. I should have written out what the normal, normal way you'd write this would be 1 minus, call that factor f. It would be f to the n divided by 1 minus f. But that's just the result for a geometric series.
And this is from 1 to infinity, right?
No, this is for a finite sum that
Yeah,
has
so
n terms.
yeah, so what I mean is like this expression is the one when we go from 1 to n, or is it the one when we go from 0 to n? Because I know there's two expressions.
This is just 0. 0 to n minus 1 is the way I've written it. That gives you n total terms, but it's a discrete number of terms. It's terms. It's not an infinite sum. Yeah. Anyhow, so here's our result, where n would be, in this case, the number of slits. For the example up there, that would be 4. Capital N would be 4. With a little bit of trig, you can convert this into sine functions instead of exponentials. And this is now defined as a new function. You remember a little while ago we defined the sinc function, and this one is called the interference function. It's not the same thing. It's easy to get them confused, but this is sine of n times something divided by the sine of just the something. So sine of n times x over sine of x. This is a sine of n phi over 2 divided by the sine of phi over 2. The interference function doesn't include the 1/2 factor. And remember, the interference function just gives us the result for the electric field. But what we're probably going to want is intensity, ultimately, rather than electric field. And so you have to take the square magnitude of that. In this case, that's just squaring it. And so we'd have E0 squared out in front, and then this sinc function squared. Here's a graph to just show you what this thing looks like for a few different values of n. If n is just 1, then it's just a straight line. This thing, that would just be sine of something over the same something. I see I'm missing a squared in the denominator down here. Where's my pencil? So this should have a 2 right there. But this is the result you get for a few terms. So if n is 1, it's just a straight line. If n is 2, it's just a beautiful sort of sine or cosine wave, except it doesn't cross the axis. It just comes down to it and goes back up again. N equals 3 has one little bump. You have a big bump and then one little bump. And after that, you get little bumps between the big ones, little peaks between the big peaks. And there are 2 fewer little peaks than the number of slits, than the number capital N. So here's n equals 3. 3 minus 2 is 1. So there's just one small peak in between each of the large peaks. I didn't show you n equals 4. That was the one we were trying to do in the lab and never quite succeeded. At least I wasn't successful when you folks were watching. But with 4 slits, you should see bright bands, and then between those bright bands, there should be 2 very dim little bands. So, so that's the result for narrow slits. But now I want to show you another way of analyzing this. First, we'll graph this. So here's the graph that I made for 4 slits, this curve right here. But what I want to show you how to do is these phasor diagrams, because I've sort of festooned it with these other little diagrams. And you have to think of how this works. We're adding up these electric field vectors. And now here, this picture is a phasor diagram. This is our complex plane with the real axis and imaginary axis. And when you look at each of these successive slits, it's got some phase shift from the first one, or from the 0th one. And that corresponds to changing its direction in this complex plane. So if we just arbitrarily set E0 to be real, right on the real axis, then the next contribution, E1, has the same magnitude. It's the same length vector. Its slit is producing the same intensity, same electric field magnitude, but there's a phase shift, and that comes through as just an angle shift in this diagram. And ultimately, we're going to add these together, so we draw them head to tail like this. So here's the phase shift on the first one. The second one has twice that phase shift, so its angle is rotated again that same amount. You could, if you wanted to, sort of draw that angle in there. I'm not sure I did it perfectly, but that angle should be the same as the angle down here. And then the last one, again, is another phase shift of that same amount. If you would continue up there and draw that angle. All those angles should be the same. And then when you stick these all head to tail, the result, the electric field that we're trying to find, is this vector over here from the beginning of the first one to the end of the last one. Now, I wish I had an animation here, but if you could imagine in your head changing that angle, that phase angle, can you see what that would do? You see how that would sort of curl the whole figure around or spread it out if you made the angle smaller. So then the trick is to try to imagine some of the special points on this plot. So first of all, begin with the point that's straight through. This is at a 0 angle. There's no, where the phase angle is 0. This is just looking straight ahead. And then everything's in phase. And so your phasor diagram is just going to be 3 of these or 4 of these arrows stuck in a row. And you square that and you get 16 E0 squared. So that's the 16 value you would get right here. Now imagine curling this around, and at some point you'll curl it around far enough you'll reach 0. The E that results at the end will be nothing because the tip will have come all the way around and closed in, and you'll have a box. Does that kind of make sense? It's a square box. It's got 4 sides because there are 4 slits. If you had a different number of slits, you'd find a different picture here that would be the first minimum. But this is the first minimum, and it's going to happen when this phase shift is 90 degrees. That would be the shift between the first vector and the next one. Each one is rotating 90 degrees from the last one. Now, if you keep rotating, if you go another 90 degrees, then you get a picture like this one, where these vectors are just going back and forth. First one to the right, second one to the left, third one back to the right again, fourth one to the left, and you've got a net result of 0. So that's this point, 180 degrees, or pi. Keep going, and you'll produce a box in a different way. Your first vector would be to the right. Your next vector will rotate 270 degrees. So I should have a smaller something here. But if you start with the vector going this way and rotate it 90, 180, 270, that's your second vector is now going down. That's this little circle there. I'm trying to show the angle there is 270 degrees from that one to the next one. And then again, 270 degrees. How do I do this? I went from there to, oh, I've got to keep going ahead and now wrap this one around to there. If I'd start with it pointing the way the other one was and then rotate it 270 degrees, I'd have a picture like that one. So you end up just building a box that goes the other way. And then at 2 pi, why then you're stacking vectors that again are all pointing the same way because there's a 2 pi rotation between each one, which ends up not really rotating it. Does that kind of make sense? Okay, then see if you can make any sense out of this point. That's a hard one to understand, but what is going on right there? Yeah, Aaron, go ahead.
Is that where, oh no, I guess 45 would be on the other side of the 90. Is that 90 plus 45, so 135?
Well, let's try it. Let me grab some scrap paper. The trick is just to try these things. So if you're thinking maybe that's, okay, here's our first vector. And then you said 90 plus 45. So that would be, here's 90. And now you want to go 45. So that would be out about this direction with the second vector. And then I've got to go 90 plus 45 would get me going down this way for the third vector. And then I have to go 90 plus 45. And this would be the fourth vector, with the result being here. And you'd have something there. And you are very close to the right answer. There isn't actually a perfect right answer. But in general, we'll see this in a little bit for a single slit. But the other picture I like to think about is, what if you went exactly 120 degrees? What would you have then? I need to be up here where you can see it. Try drawing that. Try drawing that on your paper and see what you come up with. You should be building a triangle, except that you have one extra vector. Is that what you got? You've got a triangle, and you go all the way around it once, and then you go one side further. So the result is exactly the length of one of the sides. So at 120, at the angle of at phi equals 120, what is 120 in pi language? 2/3 pi? I think so, yeah. At 2/3 pi, it means that the output is exactly 1, or it would be exactly E0. So that's what this is here, but 120 is about right here. What isn't clear from this figure is whether that's the maximum, or whether this 90 plus 45 would be a little bigger. As I draw this figure, I think it would be. I think I get a length here that's a little bit bigger than one of those vectors. So my diagram is wrong here. It goes up to E0 at that point, but it still climbs a little higher. But where is the peak? We can't figure that out very easily graphically. But you can at least understand a bit of what's going on, that you build these funny little figures that close in on themselves and give you the nulls. And then in between, you're rotating a little further, and you end up with something that has some extra that's heading out towards a maximum somewhere. It's a little hard to see exactly where it would be. And then come back down to a minimum here. Keep rotating, and then you're going to get back out to some maximum. Now I'm going to give you an assignment. What I want you to do is look at 6 slits, and using the math that we have here, and any approach that you like, I want you to make a nice plot of this, and don't just do it by hand like I did it. Get your computer somehow to print out this sort of a plot. Make it big. Do make it nice and large so that you can see all of the details. Spread it out nicely. But do it for 6 slits. According to the rule I just gave you, notice I've got 2 bumps between the large ones, 2 little maxima. That's, again, 4 minus 2 is 2. You're doing 6. 6 minus 2 is 4. So you're going to have 4 smaller peaks. They'll again be symmetric, so they're really there will really only be 2 types. There will be a slightly larger one and then a smaller one, another smaller one, and a larger one, and then back up to the big one again. But I want you to make a nice big plot of this. I'd like you to put the scale on here in terms of theta. And let's do that in degrees. You'll probably have to take some very small number of degrees because I'm trying to do this for an optical case where you've got visible light, 500 nanometers. You've got a slit. These are really closely spaced slits, 1/10 of a millimeter from one to the next. Those are quite close. That would be hard to construct. But just use those numbers to figure out what theta is. And then make a nice big plot like this. And then the trick is to go on that plot, and at the very least, for all of the nulls, you should be able to draw a phasor diagram and show exactly what's going on at that null. And then try to draw phasor diagrams for the peaks. Those will be much less clear. You'll have an approximate one, at least, for each of the peaks. I think you can do that. Now realize the whole diagram is symmetric. You notice the boxes. I got a box here going around one way, and over here I got a box going around the other way. So in a sense, once you've done half of this, you've done the whole thing. You're just going around the other way. So this isn't quite as much work as you might expect. But let me warn you about one trouble that you might have. You might not, because we're doing it in degrees, but I just want to warn you that when you try to do this, you'll run into trouble if you try to put in the exact value of one of these peaks. Do you see the trouble? You're going to have division by 0 because these peaks happen right at the value where sine of phi over 2 is 0. And you end up essentially with 0 divided by 0. And what you have, the interference function, it just has a defined value at those. There's a way of getting it. Hecht, I think, says you can use L'Hopital's rule to find what the value is right at that. But I would suggest you just avoid that by picking the numbers at which you calculate so that you don't hit those exactly. And then I don't think you'll have any troubles. I don't know if any of the programs you use would have the interference function defined. Sync function is often something you'll find, but I don't know if you'll find the interference function. You could try looking that up and see if they happen to have it, then they will have solved that, the glitch there for you. But so that's what I want you to do. Do you think you understand this enough to carry out the assignment? Do you see what's up? First, you've got to do a little bit of changing parameters. So I've given you a lambda and an A and 6 slits. And so you have to turn that using, up here, you've got A and lambda, and so this is essentially going to be a scaling between theta and phi that you would put into the formula. You'll have to use that essentially just becomes a scale factor between theta and phi. You don't even have to bother with the sine if you don't want to. We're not going to be dealing with large angles at all. These are all going to be extremely small angles. Oh, except I told you to do it in degrees, so you'll at least have to convert from degrees to radians, and then you could ignore the phi, the sine function, and just say sine of theta is the same thing as theta. But so that's a little bit of work to convert and get this all input in some consistent scale so that your plot won't be like this one. It won't have pi's. It'll have actual angles in degrees that correspond to the angle of the light beam, not the phase. This is a phase angle, and I want you to do it in terms of the angle of the light beam. So the theta angle, if you like. So that's where I'm saying you'll have to go back and forth between theta and phi here. But I give you a lambda and an A, and you should be able to do that. So make a great big plot, and then on your plot, try to draw these little phasor diagrams and see if you can explain what is happening at each point, certainly at each of the nulls, and then try seeing what's going on in the bumps. That's the idea. I don't think I want to go much further than that right now. I think I'm going to stop here because we can go on into single slit diffraction, but I'd rather, I think, have you work on this and be sure we understand this before we move on to single slit diffraction. It'll just get confusing.
I have a question.
Sure.
So I don't see why can't we just like plug the function for intensity in a software like Desmos and make it run from like 0.01 to 2 pi.
You could. I just wanted you to put the scale in degrees of theta rather than in phase angle degrees. That's all. I'm just making you work a little harder. That's all. It becomes an exercise in learning how to go from a theoretical plot to an actual experimental situation. You have to do that in real life. So I just want you to do that right away in this case here. But you can certainly, that's exactly what I would expect you to do. You'll just have to put this function in as well. And then it should all work just fine. There's nothing tricky about this. The only thing I'm saying is when you put that function in, if it doesn't have a defined interference function, if you have to put in sine of something divided by the sine of something, you're going to get division by 0 for some of your values if you're not careful. But I think if you pick your values, that won't be a problem. And that's one additional reason for doing it as a function of theta, because then it won't come out that way. Since the zeros are going to be multiples of pi, which is an irrational number, then just do your theta in units of, I don't know, tenths of degrees or something like that, and it'll never hit an exact multiple of pi, and so you shouldn't have a problem. Just warning you of that possibility. You can run into that problem. Any other questions?
Are we gonna upload this on Moodle?
Yeah, I will put the just like I did for the other ones. Everything's up there for the class we had on Wednesday, and I'll do the same thing. I will scan these papers that I'm working from right here, put those up, and then I will also put up the recording. of the class time here.
When do you want this done by?
Well, that's the question. I'd like to see if you can do that by Monday. Let's see if we can get that done by Monday so we can move on Monday and start looking at single slit diffraction. If you've done all that, if you understand it, this shouldn't take too terribly long. So see if you can get that done by Monday, and we'll talk about it. And then start moving on. So I, spend half an hour between now and then, and I think you should be able to do this. If you'll, I hope you all have printers available that you can print out a function of some sort. I don't want you to have to copy it from a screen or whatever. Yeah.
Do you have a program you would suggest using to do that?
I don't. I'm not the expert. I wish I was. I have not gotten up on the various methods. I have all kinds of programs I've used in the past, but I would not recommend most of them to somebody starting out. So I would say talk to your classmates would be one possibility. They probably know more than I do about what's quick and easy. This you could do with a spreadsheet if you want. There's nothing in here that requires anything advanced. You could do this in Excel if you wanted to. It's not necessarily the best, but if you know it, I do all kinds of dumb stuff in Excel times when I just want to knock something off quickly and I know what I'm doing. But no, you could use MATLAB or Octave if you've got that, or any computer language would do this. Well, not any, but many computer languages would do this. Shoot, what else?
GeoGebra.
Yeah, you could probably do this on Mathematica, or even not going as far as Mathematica, but just what's the online version of that? What's that again?
CoCalc.
CoCalc. Yeah. Yeah, that would be a fine, as long as you can make some kind of a graph, and then I don't know, can you export it back to your computer and use it somehow? I don't know what it allows you to do, but yeah, I don't have a particular one to recommend, Aaron. One of my favorites is one that nobody's ever heard of, but something called MathCAD that was developed a long time ago, and only exists because there is one fellow in Eastern Europe that has programmed a free version of it out there. And now I use that sometimes. But Ben, you have to turn your mic on.
Their website looks nice.
Who's that?
The MathCAD website.
Oh, MathCAD. Yeah, you got to pay a bundle for that. So you go off to this fellow. I love that program. It has a couple of things that I wish were different about it, but it's a great way of doing calculating for engineering kinds of things, because you can put units in and ask for an answer in certain units, and it does the conversion for you. It's just really wonderful that way. And you write the stuff out in a form that looks recognizable. You essentially write it the way you would write it on your paper. So it's kind of a neat package. But I'm trying to remember the name of it now. The guy that's got this free one out there. See if I can find it. I have it on my computer, but I've forgotten the name of it now. I don't know, Google free alternative to MathCAD and you should be able to find it.
Is it called BlockPad?
Nope, that's not the one I've used.
Maxima?
I don't think so. That doesn't ring a bell. I mean, it really is a clone of MathCAD. It's not an alternative. It's a SMath. That's the one. But I don't know where to get to it. Yeah, I don't know. Well, anyhow, I haven't looked at this for a while. So I probably shouldn't be making recommendations right now. So, all right. Well, I think that's all I wanted to do today. So take a look at that. See if you can create some plots, and we'll see each other again on Monday at 2 o'clock. And see if we can work our way into this chapter. It's a beautiful chapter. All kinds of wonderful stuff in here. So. I hope you're all doing well.
I just had a quick question about projects.
Yes.
So I was thinking of something and I don't know. So
Yeah.
I was looking at different things with eclipses. And I think it'd be interesting just to look into that and then look at what people, like the weird ways people have tried to view it and like homemade devices that they've used.
Oh, you mean
Try to-
solar eclipses?
Yeah, yeah.
Ah, okay. I was thinking lunar eclipses for the moment. I was trying to figure out what you meant. But yeah, okay. Yeah, trying to look at solar eclipses in different ways. And yeah. What tell me more about what you have seen and heard.
So from the few things I've seen, there's people that have made like little boxes,
Yeah.
tried to do it, and then
A pinhole camera is what that is essentially. Yeah.
and then they've had it where the different like mirrors where it projects onto a different surface, and they try to do it that way. And then there's some people that have tried with like smoke and trying to just, I guess, kind of shade it using that.
Oh, interesting. I haven't heard of using smoke. Okay. That's new to me. Another one you should be aware of is using either a telescope or binoculars.
Mm-hmm.
You can make a very good image. That's actually the best way. The best way. It's one of the best ways. It certainly is the best if you want to have a group of people sharing a telescope or binoculars. I mean, everybody can have their little filter that you look at it directly, but to have a magnified view that a whole group can share, you can simply project it. And I do that all the time. When you're trying to show the sun, you can make a projection using any pair of binoculars or telescope. You do what you think you shouldn't do, which is you aim it directly at the sun, and then hold a piece of paper instead of your eye, and you hold it some distance away, and you can choose to make the image as large as you want. And the larger you make it, the dimmer it is, and so you just have to kind of decide how much you want to try to shade it so you can still see it. You can make it quite large that way. There are some concerns if you're doing that. You have to be careful of what type of eyepiece you're using. And I'll let you find out why.
Okay.
Because you can destroy your eyepieces that way, or at least damage them. And that's an interesting tale in itself. That's got some interesting optics in it that you should begin to understand pretty well by now. So, so you can learn about that. When astronomers use, even when I just go out to do observing before the sun goes down, you can use your telescope and make an image of the sun, and that's a great thing to do. But you have to choose your eyepiece carefully at that point. I don't think with just binoculars it matters so much. It's when you have a larger telescope that it starts to become an issue, that the eyepiece can get damaged if you're not careful. But there are certain types of eyepieces that are immune to the problem, and they're the older types, it turns out. So yeah, no, that would be a fine topic. Go into that as much detail as you can find.
All right.
See what you can learn about it.
Mm-hmm.
Yeah. Anybody else have any thoughts?
Still pursuing my 2 ideas.
Okay. All right. Well, take a look at this assignment. Keep thinking about your project, and I'll see you again on Monday. Okay. Bye-bye.